All right, so I'm going to work this problem here. This is a special request. This particular problem was from, test. Oh, come on, you can write for me, buddy. Okay, chapter 5, honors test from 2023 to 2024. And I got those requests for while studying for the finals. Just kind of an understanding of what's going on here. Okay, so let's start with what we know. We've got this block. It's starting up here at point A. And let's see, what do we know? We know the mass is 20 kilograms. That's 3 sig figs. The spring has a spring constant. Okay, so the spring is over here. 50.0 newtons per meter. The entire track is frictionless. Find the maximum compression of the spring. So basically, it's going to be dropped at A, and it's going to come down here and compress the spring. Okay, I'll call that full compression. If I kind of scribble that thing in there, I'll call that a position D. Okay, so let's go ahead and let's work this particular problem. So already, this is a work and energy problem, and it is not asking for anything that has to do with work due to gravity. So I know I'm going to use the work non-conserved equals the change in kinetic energy plus the change in potential energy, right? Okay, so as the block is sliding along, anywhere along there, which forces do we have? So if I draw a free body diagram at anywhere in here, we will note that it's got a normal force and it's got gravity. Okay, and for this particular part, it's frictionless. So those are all of our things. We will note that the normal force is always perpendicular, so it does no work, so we're not interested in that. Because this is a work problem, that's going to go right there. Okay, so the force of gravity is going to go into the potential energy. So because of that, there's nothing to go into here. So there will be no non-conserved energy between A and D. Okay, A and D. Okay, now we're going to note, so for change in kinetic energy, well, I need to know change in kinetic energy from A to D. So D is the final position over here. We'll note that when it squeezes all the way in there, it is no longer moving. Okay, so V equals 0 when that thing squeezes all the way in. Maybe I'll zoom in a little bit. There's no reason to have the entire problem in there. So the final kinetic energy is 1/2 mass times 0 squared. Okay, so the initial kinetic energy up here, well, it's going to be dropped from that position. So V is 0 there. So we're going to minus the initial kinetic energy, m times 0 squared. Okay, again, so there's no change in kinetic energy. All right, so then what about the potential energy? Okay, well, this is the object right here, but when the object is right here, we have another force, right? We've got the force of the spring, okay? And that one will also be treated as a potential energy, right? Because both gravity and springs are conserved, okay? So they're both going to go into the potential energy. So in other words, I have to split this thing out into forces due to springs energy of springs and energy and potential energy due to gravity. Okay, so let's do, let's do gravity first. Okay, so we know that the potential energy due to gravity is going to be mg times the change in height. Okay, I think for honors it's delta y, mg delta y. Okay, which we happen to know that delta y is this number right here. Okay, it turns out to be a negative, that number, right? Because it's going from A to D. All right, so, and then we need to do the spring, okay, plus the potential energy due to the spring. So we'll do final minus initial. So we'll start over here, where the potential energy due to that spring depends on its position, right? X equals unknown, that's what we're solving for. Okay, so the potential energy due to the spring right here is 1/2 kx squared. Okay, now it should be obvious that the potential energy due to the spring up here is non-existent. Okay, so we'll do final minus initial. Okay, 1/2 kx squared minus initial. Final minus initial. Okay, so let's see. So all of this goes away because there's no kinetic energy. This mass can't cancel out, unfortunately. So let's see, let's rearrange this. Do we want to, yeah, what do we solve for x squared? Okay, so I'm going to get negative mg delta y equals 1/2 kx squared. Let's see, negative 2mg delta y equals kx squared. So let's divide by k and take the square. Okay, negative 2mg delta y divided by k square root equals x. Okay, so I'm going to go ahead and plug numbers in there. X equals square root of negative 2. What was the mass? Mass is here, k is here, 20 and 50. Let's see here, 20 kilograms. Ooh, MGM. See, you say yourself 20, 50, and then you just start writing 9.81 meters per second squared. Delta y in this case is negative 0.5. Dadgummit. Okay, oh no, that's 1 sig fig. That's horrible. Okay, anyway, I guess we'll deal with that. And then the k. Now remember that delta y is negative because the final y position over here is 0 and the initial y position over here is 0.5. Okay, so it went down. Okay, and then the k is 50 newtons per meter. Okay, and then just to check my algebra, one of the key things here is to make sure that the units work out. So, all right, so sorry I have to use my phone as a calculator. I don't have a real calculator around here. So anyway, so we get 196.2 on top and 50 on the bottom, and the units are, let's see if we can track this. Okay, kilogram meters per second squared, so that's a Newton times a meter on top, and on the bottom I've got newtons per meter. So all told, if I start scratching stuff out, it's for some reason I wanted to do it in white. Stop it, you jerk. Okay, here we go. So the newtons cancel, and I'm left with meters squared on top. So x equals the square root of 3.924 meters squared. So x equals, let's see, raise that to the half power, and we get 1.9809 meters. Unfortunately, there was 1 sig fig on this stupid question. And I probably told you something else in person, because who wants an answer like that? But whatever. At least in this case, it's not so big of a round, so I think we're okay with that. Okay, so hopefully that makes sense. So basically, while going from A to D, okay, potential energy due to gravity got converted into potential energy in the spring. Okay, and there was nothing lost because there was no friction, there was nothing gained because there was nothing pushing on it. So that's what happened in part A, or in question A. Okay, question B. The entire track is frictionless except for the 2 meters between points B and C. So right in here, where the coefficient of kinetic friction is. Okay, so we're going to call that L. L is going to be 2 meters. The coefficient of friction, mu, I guess technically this is mu k, is 0.03. Find how high the block rises after it has hit the spring twice. Okay, so let's see. Let's go over here. I'm going to redraw this. It's going to be a little sloppy, but, that thing was getting a little bit messy. Okay, so here's the block. It's at position A. Here's the spring. All right. Okay, and so what the block is going to do, and I'll do this in red. There's a little rough patch in here somewhere, right? Okay, so what the block is going to do, and I think this should be fairly clean. It's going to cool down here. It's going to smack that thing. It's going to compress it. Okay, some distance, and then it's going to fling back up. Okay, it's not quite going to make it as high because this thing is going to take some of its energy. Okay. So it's going to end up at, I don't know what we'll call this, a point. I don't want to use a point that's already been called. We've got, let's see, we've got A, B, C, D. So we'll call this point E, right? And then it's going to go back down. It's going to compress the spring, not quite as much because this is going to take energy. And then it's going to come back up, and now it's going to end up at a point somewhere on the, dadgummit, horrible drawings. Okay. These are both horrible. All right. So the first time it comes up, it doesn't quite go as high. It goes to E. The second time it goes up, it's now going to be at a position I'll call F. Okay. So, and obviously, or maybe not obviously, but each time it does that, it's not quite going to make it as high. And eventually it won't even make it off of that real rough patch right there. All right. So basically, if I'm going to kind of put in here what I know about this particular spot, I know this is 0.5 meters. I know this sucker right here is L equals 2.0 meters. And there's a mu of 0.03. So again, I guess 1 sig figs. All right, so now what I want to do, and you could do this a few different ways because we just solved the A part of this problem. You could start your problem here if you wanted to. All right, you could go from, what do we call that point, D? I could go from D all the way to F, right? Now that would be an interesting path because it would be, let's see, so it would go D to E, then E back down to D, and then D back to F. So it would cross this thing 3 times. Yeah, I don't particularly like that. I'm not going to do it that way. The reason that I'm going to do that, I'm going to start at A and I'm going to go to D. And the reason for that is because I'm going to start at A and I'm going to go to F. And the reason that I like that is because A has given information. We like to start from the very beginning. Okay, so again, I'm going to use work non-conserved equals the change in kinetic energy plus the change in potential energy. Okay, so now that we're staring at this, we want to think about this thing from A to F and how it is, moving and whether or not it's losing energy or gaining energy. Now, I know it's losing energy because this thing right here, this little patch right here is taking energy each time it passes it. Okay, the cool thing here is the spring is neither adding, not adding, or subtracting. Right? It's not doing any non-conserved work. And the reason we know that is, well, first of all, just from class, but also, the block hits it, it gives the energy, the spring kinetic energy, the spring takes the kinetic energy, stores it briefly, and then gives it back, right? So, because it's a perfect spring, okay? So in other words, if I were to do a free body diagram of the block as it's moving along here, okay, so here's the block at any random point along those things. Okay, I'm just kind of drawing it as if it was like, say, right up there. What forces would we have? Well, let me see. Let me get a different color. Will it give me black? Yeah, give me black. Okay. So we've got gravity going this way. I've got the normal force going that way. And during this point of the thing, right, it's got friction, which is going to oppose its motion, right? Obviously, over here, the friction would be going, directly to the right. Over here, there is no friction, right? But the point being that these are the forces that I need to think about, right? Technically, there's a spring force in here, and so I could include that as well. So in doing a little free body diagram here, I could put a little force of the spring that's going that way. And the point here is not, a rigorous free body diagram, because really I would need one here where there's no energy being lost. And I would need one here where there is energy being lost. And I would need one here, right? And that's a lot of free body diagrams. The point is I want to think about the forces that I have to deal with. And so I've got a normal force, I've got a spring force, I've got a friction force, and I've got a gravitational force. All right? And so, what I'm going to do here, now that I know that these are the 4 forces I'm dealing with: normal, friction, spring, and gravity. Okay, those are my 4 forces. Okay, so first thing, okay, normal force is perpendicular to the motion, so it does no work. Okay, so I'm not worried about that. Okay, force of friction. This is, I don't know how to put, opposite the, it is parallel to the, movement. Like if we look at this object right here, the force of friction is going this way when the object's going that way. However, it is in the opposite direction, so we'll do negative work. Negative, non-conserved work. All right. All right, the force of the spring. Well, the force of the spring is conserved, so this would go as a potential energy, right? However, I will note that because I am doing this problem from A to F, or really from A to F, okay? At neither A nor F is there any potential energy due to the spring. Potential energy to the spring is 0 here. Potential energy to the spring is 0 here. So because I've chosen my problem to go from A to F, the potential energy here is going to be 0 at A and F. 0 at A and F. Okay? Now, the force of gravity, we know this to be, that's a potential energy. Let's see, this be, and it is not 0 at A nor at F, okay? So this is really the one that we need to deal with. Oh, and we need to deal with this, right? So these are the two that are going to go into my equation. Okay, so let's go over here, and let's see here. So work non-conserved is going to be negative force of friction times the distance it travels over this particular rough patch, right? And so as it goes from A to F, it goes over that patch once, twice, 3 times, 4 times, okay? So it's going to be 4 times the length of the patch. All right? Okay, cool. Kinetic energy. Let's see. At both A and at F, this is getting really hard to see now, but both at A and at F, it is at its highest point, or at least I guess it's at rest in both of these cases. Like this one's at rest because it gets released from rest. This is at its highest point because it's at its highest point before it goes back down. V is 0. So at both kinetic energy, at both of these locations, the final kinetic energy, that's going to be the, based on what's going on at F is 0. And then based on what's going on at A, it's 0. Okay? Now we're going to do the change in potential energy. So I got potential energy at F, because that's my final. All right? It's getting really hard to see under there. Let's see here. Here's F. Okay, so the potential energy at F is, well, we've got a height here. All right. Okay, and I don't know what we want to call that. Let's call that Y at F. Okay, so I've got mg delta Y, right? Where this is Y, sorry. This is equals Y at A, right? So the delta Y will be YF minus YA. We're expecting a negative number, right? It went down. Okay, so there's our equation right there. Again, you could have done this from D to F, and that would have worked. But it would have only crossed this patch of friction 3 times, and you would have had spring potential energy going to gravitational potential energy, right? I just prefer this way. Okay, so let's see here. So let's start working through this. Let's delete that. Okay, can I zoom in? Okay, so the force of friction in this case, this patch is nice and level, so when it's nice and level, the normal force is just mg. Okay, so negative mu mg, mu times the normal force, times 4L equals mg delta y. Let's see here. It looks like those m's are going to cancel. Oh, those g's are going to cancel too. Okay, so delta y equals negative 4 mu L, is that right? Is it that simple? 4 mu L? I suppose it is. I mean, certainly the units work out, so that's always nice. All right, so the delta y, I guess we can do it this way. So there's 2 ways you can do it, maybe not obviously. You can either plug in right now and say, oh, look, delta y equals negative 4 times 0.03 times the length of the patch, which was 2 meters. And then say delta y equals, what's that? 4 times 2 is 8, times 3 is 24. So negative 0.24 meters. And then you go up here and look at it and go, okay, well, we started at 0.05. So if we go down 0.24, I'm going to get YF is 0.26 meters. Totally reasonable. Or you could expand delta Y, and you could say, well, that's Y final, YF, minus YA equals negative 4 times 0.03 times 2 meters. And I guess for that YA, we know that your initial height is 0.5 meters. So then when you plugged all that in, you would get YF minus 0.5 meters equals negative 0.24 meters, and then you would get YF equals 0.26 meters. Okay, so that's how we do the B part. All right, boy, look at that. Wow. Hopefully that made sense to you. It sure looks ugly up here. All right, although this one's starting to look ugly too. Okay, find the final position of the block in terms of the distance from point B. Okay, so again, I'm going to draw another picture. Here we go. Okay, so we've got our little rough patch is in here. Okay, it's completely level, despite what my drawing might show. Okay, there's a spring right here. Okay, and the sucker is going to be dropped off up here. Okay, so this is position A. And wherever it's going to finally stop, right, say here, I'll call that position G. Okay. So this is a little bit, this is one of my favorite problems ever. Where does it finally stop? Okay. Now again, I guess we'll put the important numbers on here. So we'll put, this is, let's see, this is 0.5 meters. And this is 0.2 meters. That's 2.0 meters. 2.0 meters. And then, oh yeah, and this is mu equals 0.03. All right, and that's all we really need here. Do we need the mass? We probably need the mass for this sucker. It might cancel out. I think it cancels out, but we'll go ahead and put it there. So the mass is 20.0 kilograms. All right, cool. So now it's going to go from A to G. Now, how's it going to get to G? Well, it's going to slide there, right? So it's going to go like this. It's going to hit this thing. The thing's going to give it its energy back. It's going to go up. It's not quite, it's going to make it to, I don't remember what we called that point. And then it's going to go back down. It's going to hit this thing, and it's not quite going to make it as high, right? And the reason it won't make it quite as high is because it's losing energy every time it crosses this thing. So it's going to go here, and it's going to come back, and it's not quite going to make it as high. And eventually, it's going to get stuck, right? Technically, sorry, I didn't draw these on the thing, but each time it's going to not quite make it as high. And then one of those times it will simply just not make it, right? And each time it's because it's losing energy here. Okay? So, did you hear that ding a second ago? That was me getting an email from the student who asked for this question, telling me they wanted a different question. So anyway, I hope that he looks at this video since I made it for him. I'll have to make a second one. All right, so anyway, let's see, what do we got here? All right, so we're trying to figure out where it's ultimately going to stop. And so basically we just need to figure out how much energy it needs to lose in order for it to come to a stop. Okay, so I'm going to go from A to G. Okay, A to G. Okay, let's see here. So again, free body diagram anywhere along here. What are the forces we're dealing with here? Okay, so the forces we're dealing here, like if I draw the block, let's see. So at different points, I have springs, I have gravity, I have friction, which could go left or right depending on which way it's moving. I've got a normal force. Okay, these are all the forces that are going to act on that thing in this particular problem. Now, let's consider them all in order. I'm putting the normal force first because it is the easiest one. The force of friction, the force of the spring, and the force of gravity. Okay, so the normal force is perpendicular, so work is 0. Okay, the force of friction, well, it's perpendicular, but it's always going in the opposite direction of the motion. So we're going to have work non-conserved, which will be negative. The force of, I can't tell if that's a G or an S. Let's call that an S. The force of the spring, that is conserved. Okay, but PE of the spring equals 0 at both A and at G. Okay, so it's going to be 0 for this particular problem. And then the force of gravity is going to be, well, that's going to be conserved. And A has potential energy due to gravity, and G does not if I set y equals to 0 to right there. Okay, so we will say, I don't know what we're going to put here, potential energy due to gravity. Okay, so it must be taken into account. Okay, so if I'm going to A to G, I'm going to say work non-conserved equals the change in PE plus the change in KE. Okay, so work non-conserved, the only non-conserved work I have is right here. Okay, and I guess I got to worry about these two, right? So one's a potential energy, one's non-conserved work. Okay, negative force of friction. Okay, now I have to deal with the fact that I need a distance, right? Force times distance. So I don't know how many times this thing is going to pass over that particular block, right? So I can either just solve for the total distance by just calling that x, which is what I think I'm going to do. Alternatively, I could just put n for the number of passes times L for the length of the block. But I think just using x is probably the way to go. So this is the distance it travels over that thing. So it might be 2 meters, 2 meters, 2 meters, 2 meters, so that's up to, 8 meters, 10 meters, and then maybe it stops at 11 or something, right? So that's what we're solving for. Okay, so, this is backwards of the way that I usually do this. My apologies. Delta KE plus delta PE. Okay, now remember we're going A to G, and we'll note that it is at rest here, and it has stopped when it is here. So there is no kinetic energy at either position. So final at G has no kinetic energy. Initial at A has no kinetic energy. All right, now, potential energy. We do not have potential energy of a spring because there is no spring potential energy at A or G, so I'm not going to bother with that. Potential energy due to gravity, however, we've got mg delta y. Okay, and I know the delta y here is going to be a negative 0.5 because it ends up at y equals 0, and it starts at y equals 0.5. So that delta y will be negative 0.5. All right. So before I move on, I'm going to expand this force of friction into negative mu mg. So that's mu times the normal force times x equals mg delta y. Oh, this is coming out nice and pretty. Let's see here. So m and g are going to go away. M and g are going to go away. So delta y equals negative. Oh, wait, I'm solving for x here. Sorry. X equals negative delta y on mu. So x equals negative 0.5 meters. Now remember it's negative because we went, the final was below the initial, divided by 0.03. And x equals 16.667 meters. Okay, which basically means it went 2 meters. 2 meters, that's 4, 6, 8, 10, 12, 14, 16, and then 0.667 that way. So on our patch, it ended up 1.33 meters from this side and 0.67 meters from that side, right? So that's where the point G is, where it stops. Okay, now how did it ask the question? In terms of the distance from point B. So point B is right here. So it is 0.7 meters from point B. Okay, or to the left of point B or whatever, right? Okay. Okay, so that's the problem. I'll go ahead and upload this one, and then I guess I'm going to work on the other one. Thank you for ruining my weekend, sir. I'm kidding. It's okay. Anyway, hope this was helpful. All right, bye. Now let's zoom out and see the mess that we've made. Yachi machi. Whew, beautiful.